The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon and welcome to the Aculon NanoClear webinar. Today the focus of the webinar is why stencil nanocoatings are not just for fine pitch stencils anymore. During this webinar we'll give you an overview of the technology, and you'll see, as you can see in the global SMT cover featured on the start of this webinar, why we believe that stencil nanocoatings are at a tipping point and should be used across a broad range of stencils. My name is Edward Hughes. I'm the CEO of Aculon and the producer of the NanoClear Stencil nanocoating. Joining with me today is Chrys Shea, the president of Shea Engineering, an independent consulting firm who specializes in the surface mount technology printing, and she has over 25 years of expertise helping companies improve their printing process and has been studying nanocoatings for the last 5 years and is generally regarded as the leading expert in nanocoatings in this SMT industry. During the presentation today, we're going to give you an overview of nanocoatings, talk a little bit about some of the benefits, and share with you the cost and payback calculator. That's the key feature of this article in Global SMT this month. We're also going to share with you some new documented performance improvements from real examples from CEMs and the studies that they've done. We'll also address a question some people have is, does the wipe process coat the aperture sidewalls? And you'll clearly see that it does. And we'll share with you some best practices in cleaning and durability that we've learned over the last 5 years of having this technology in the marketplace. Some of you are aware also there's some choices in terms of nanocoatings. There are fluoropolymer nanocoatings and SAMP nanocoatings, and we'll give you a compare and contrast that, as well as give you a sneak peek at the next generation of product that we are talking about launching. Finally, we'll talk a little bit about distribution and availability, and then we'll hopefully leave plenty of time for questions and answers. This webinar is being recorded, and a copy of the recording will be available for viewing and download on the Aculon website. In addition, all registrants for the webinar will receive a copy of the presentation. And during the webinar, if you have questions, please look at your control panel, type the questions into the control panel, and we'll try and tackle as many as we can at the end of the webinar and address any specific questions you have. We'll also obviously provide you contact information to follow up with us if there's any specific follow-up questions. So let me give you a very brief overview. Stencil nanocoatings are basically extremely thin flux repellent films that apply to the bottom side and aperture walls of stencils. Here you can see the two-part process that is the Aculon NanoClear product. Part A is a primer and Part B is the treatment itself. And what we've seen over years of now being in the marketplace is that our customers have been able to improve the quality in terms of higher yields, better transfer effectiveness. They've been able to boost their productivity with reducing the amount of frequency of under stencil wiping, and also that allows you to reduce the downtime caused by paper changes. We've also seen that we can reduce the costs. There's less rework, both complex and simple rework, and there's lower consumption of both paper and solvent in doing this. Now, what is interesting is we believe that nanocoatings are basically at a tipping point now that they're about to be broadly adopted across the stencil printing business. As many of you are aware, technologies when they're adopted often face early resistance, partly because of price pressure to not wanting to increase cost in adopting new technology, partly because of resistance because engineers feel the current process is meeting the needs and good enough. And so as you look at this technology, it's rapidly growing, and we'll get to that tipping point, as other early technologies did as well. Some of you remember when chemically etched apertures were the norm, and now obviously everybody's using laser cut apertures. Some of you will remember when generic mill grade stainless steel was the norm, and now basically specialty alloys have become the predominant foil in the industry. Similarly, chemically etched single steps were the norm, and now people are much more used to machine or multi-level steps. So we believe that these technologies are similar, with the one exception that the SAMP nanocoatings have always been very affordable, and so it's not really a price issue in terms of getting into this marketplace, as opposed to people understanding and seeing some of the benefits of this. And that's why we believe that the Global SMT and Packaging Magazine put this article as the feature article and on the cover of this. They believe that they're seeing across their business and the industry that a broader scale adoption, and this is really a tool now for people to basically improve their printing processes. We've experienced ourselves many conversations with customers that are saying, yes, I use your nano coating on fine pitch stencils only, or the hard to print stencils. And what was interesting is when we explained to them there are a lot of benefits that can be done by using the nano coating across all the stencils. There was a little bit of a show me. So we asked Chrys Shea, as I say, an independent expert, to put together a cost-benefit calculator to basically give hard numbers to those quality statements and hard numbers to the paper savings and other savings that can be done. And so Chrys, you've done a lot of work putting together this great calculator. Why don't you show us a little bit about what it can do?
All right, thank you, Edward. And as Edward mentioned, I've been a process engineer for 25 years, and the first 12 were on the user side, where I had to justify equipment upgrades, new equipment reconfigurations, and look at different ways to cost justify these things and show their payback. So he enlisted me to try to capture some of and quantify, monetize some of the benefits of NanoClear stencil treatment. So I looked at 3 different categories of benefits. You benefit in quality in terms of higher yields and better transfer effectiveness. When we say transfer effectiveness, we don't necessarily mean transfer efficiency. We'll show you pictures where you see much crisper prints, less slumping prints, and we also consistently see a 2 to 3 point drop in variation when we nanocoat stencils. We also mentioned productivity, because when you use a nanocoating, you can reduce your under stencil wiping, which means less downtime for wiping in general if it doesn't meet the takt time of your line, and less downtime for paper changes, assuming that when your printer goes down to get your paper changed out, the rest of the line is starved waiting for the printer to come back up. And we all know surface mount lines aren't cheap. And ultimately, the cost reduction is a combination of both the quality and productivity improvements. You're going to spend less money on paper and solvent usage, and you're going to perform less rework. So now, how do we characterize the different PCB assemblies out there, because there are so many different configurations? Well, I took one cut by looking at component population density. Now, if you look at the bottom of the screen down here, we'll see 1 check mark indicates you should see a measurable improvement. 2 check marks means you should see a substantial improvement. And if there's no check mark, it's basically a draw or a push, or maybe benefit that's not really truly spectacular, remarkable. So when we look at component density, if you're running a high density PCB, that means you've got a high aperture density and a lot of small apertures most likely. So that's where you're going to see the most benefit. You'll see the higher yields, the better transfer effectiveness. If you're running high density, high aperture density, you're probably wiping more often than the guys running medium or low density, and so therefore you will definitely consume less paper. And because of the higher yields on the high density boards, you'll see a lot less rework. So pretty much every category is going to give you substantial improvement if you're running high population density circuit assemblies. If you're running medium population density, well, you're still going to see a big improvement in terms of yield and transfer. You may not see as much improvement as reduced underwiping and less downtime, just because your board design doesn't dictate as much as it would on a high density assembly. Therefore, you wouldn't get as much benefit in paper and solvent consumption, although it would still be measurable. On a medium density board, I think you're still going to see a substantial improvement and less rework. Low density boards, the simpler boards to build, you're still going to see a measurable improvement across the board. No pun intended. It really doesn't matter the component density, population density of the PCB. No matter how you slice it, you're going to see some improvement. Now, another way we looked at the PCBs was by the component mix. Some of us build really small stuff, portables. Some of us build really big stuff like servers or backplanes, and some of us have the mixed blessing of building broadband technology where our designers will throw a QFN, 0.5 millimeter QFN, right next to a huge 2000 IO BGA and expect us to build it. But if we look at component mix, again, if you're building the really small stuff, you're going to find the most substantial improvement from using NanoClear. That's because your apertures are smaller, they're easier to clog up, you're more likely to get bleed out on the bottom of the stencil with your flux, and you're probably wiping a whole lot more often if you're running highly miniaturized stuff. If you're running broadband boards that combine the finer and coarser pitch components, you'll definitely still see a substantial improvement in higher yields, which equates to less rework, and you should definitely see a very measurable improvement in the other categories. If you're running really easy, class 1 type stuff, component pitches are all greater than 0.5 millimeters or 20 mil pitch, you'll get a measurable improvement in yields. You'll definitely be able to reduce your underwiping a little bit. So the yields would equate to less rework. If your pitches are greater than 0.5 millimeter, in general, you should not be having release problems. You will get better transfer effectiveness, but it won't be marked or substantial, because if your process is running in control and you're running with decent paste mediums, you should be able to print things greater than 20 mil pitch without any problem at all. You still will, however, benefit from the reduced underwiping, and you should still get some better quality. Now, the third way we characterize circuit boards was by the component type. If you're really out there on the leading edge, you're doing the 0.4 millimeter pitch leadless BGAs, QFNs, package on package, the 0105s. Again, because these apertures are so small and so densely packed, that's where you're going to reap the most benefit in terms of the quality and the productivity. If you're working with the challenging new packages, and when I teach classes at the conferences a couple times a year, and I go around the room and I ask people, what they're here for and what their biggest problems are. And the past 2 years, I've heard a lot of people talking about the 0.5 millimeter pitch BGAs really starting to hit mainstream and eating their lunch, and also the high IO BGAs. And some folks are just now starting to struggle with the 0201s. Again, because these are apertures that are usually in the 10 to 12 mil or less range, you're going to see a lot of payback, a lot of improvement in your quality and your productivity. If you're kind of in that generic mainstream SMT where your finest leadless pitch is greater than 20 mil or 0.5 millimeters, if your gall wings or leaded pitches are better than or equal to 16 mil or 4.4 millimeters, if your chips are 04 or 2 or better, you'll see measurable improvement. Again, this is part of why we say that NanoClear is not just for fine pitch anymore. Obviously, the finer the pitch, the denser the board, the more miniaturization, the more benefit you will get, but that's not to say you will not reap benefit on general SMT boards. So what we're going to do now is I'm going to introduce you to the spreadsheet that you can download either from Aculon.com or from SheaEngineering.com. It's on a rotating banner. It's one of the 3 that you can just click and download on if you go there. We had a couple charters when we made this. It had to be a very simple calculator. We did not include anything about machine cost, depreciation. We did not include anything about indirect labor, which are very difficult to quantify, especially at the engineering level. And also, the payback on this was so straightforward, we really didn't need to dig too deep into those type of areas to be able to show a payback. The spreadsheet I'm about to show you is customizable. None of the cells are locked. All the calculations are transparent. You can see them in the formula bar. It's formatted right now in US dollars, but it can work in any currency you like. And what it will return after you input some of your own information is the number of prints, how many prints it will take to pay back the coating of your stencil, and it's going to show you the bonus extra uptime you'll have per year from not taking that line down when you change the paper. So right now I'm going to exit out of this screen and pull up Excel and start here. You'll see it's a 3-tab workbook. The third one is the benefit matrix that I just went over with you all. So if you want a little guidance on what to estimate for improvements, you've got that there. This first tab is the cost savings calculator, where we put in our current yield, our projected yield, what our wipe frequency, what our projected wipe frequency is. And down in this area here is where you'll see the cost reduction numbers that feed in through this cost calculator tab here. So the place we want to start is on the cost calculator tab. On the left column of the cost calculator tab, we're trying to calculate the cost of rework, and on the right-hand column, we're calculating the cost of consumables. So when we define simple rework versus complex rework, simple rework is considered something that a lower skilled operator can do with hand tools. Soldering irons, wick, braid, solder sucker, something along those lines. Does not need any special machines. When we talk about complex rework, we talk about things like BGAs, LGAs, QFNs that have to be performed on dedicated rework machines, which are expensive, we know, but they're not being counted into these calculations. So when we look at the cost of simple rework, we put in the time required in minutes. I put 4 minutes in there as a default, and you can change it to whatever fits your operation best, but it's the time it takes for the operator to look at the board, find the defect, or the AOI machine to kick it out so the operator can log in the defect, fix the defect, and then log that defect into the defect database. So I've got that estimated at 4 minutes. You could easily change it to 3 and see what happens, or you could change it to 5 and see what happens. So it's really, really nice and easy to play with, especially as you're presenting it to management. Now the labor rate for simple rework is typically less than for complex because it requires a lower skilled labor, and around here about $12 an hour is what soldering operators are being paid. So again, that can change based on your geography or your company's business model. The benefit rates are 25% and the overhead rate is 25% here. I got that from a finance director who said that's what they run in their chemical company, sort of an adjacent industry to ours. Depending on whether you're a contract shop or an OEM shop, that benefit rate will definitely change. Depending on your geography, that benefit and overhead rate may change too. But again, you can change it. If your benefit rate is only running 20%, that's great. If you're in an area where it's a high cost of doing business and your overhead is at 30%, that's great. You can just simply go ahead and change it however you like. And that will give you the cost of reworking one solder joint right there. Now, when we talk about complex rework, we're talking about something like a BGA, an LGA, a QFN. They typically have discretes around them, so you have to either remove the discretes or shield them. You have to put that board in the machine, pull the part off, clean and redress the pads, sometimes reball the BGA, put the device back on the board, solder it back down, and then unshield or replace any of the adjacent components you pulled off. That can run anywhere from 20 minutes to an hour and a half. My estimate in here right now is 60 minutes. Again, it's in the white cell. You can change it to whatever you want. Say you think it's only going to be 45 minutes. The labor rate is about 25% higher because it does require a more skilled operator. Again, you can change that. And the benefit and overhead rate, again, you can change to whatever your company's model is, and those are really easy numbers to get. Probably the hardest part about getting them is finding out who your plant's cost accountant is, and then just sending them an email or making a phone call and saying, hey, what's our benefit and overhead rate out here on the shop floor? So I'll just put that back to where I had it for now. So this gives you your cost of your simple rework, your cost of your complex rework. This is going to be important when we go to the savings calculator page. This is also a very simple and effective way to calculate the cost of your defects if you're trying to justify new machines, better consumables, better solder paste, better wiper paper, improved solvents. You can easily show the payback by calculating the cost of your defects. Now, when we talk about paper and solvents, again, these are pretty typical numbers. Paper typically costs around $20 US per roll, depending on how many you're buying and who you're buying them from and if they're decent quality or not. I know the rolls come in different sizes. I picked the 10-meter roll. And we look at how many millimeters we advance per wiper pass on the paper and the number of wiper passes in the cycle. These are program parameters that are in your printer. If you're the engineer in charge of the printer, you probably programmed them and know them off the top of your head. If you're not the engineer who programmed the printer, you can simply go ask the engineer or just go look at it on the printer's menu and find out what your advance rate is and how many passes you make. So this 3 cents here is about, on a typical 3-pass, like a wet vac dry pass, advancing 5 millimeters per pass at a $20 roll, you're looking at wiper paper at costing about 3 cents per wipe. When we look at wiper solvent, assume we're paying about $30 a gallon. We're in SI units here, so there's about 4 liters per gallon. How much do you use on each wipe? We did a few tests of what was being dispensed and came up with anywhere from 1 to 4 milliliters. I've got 2 milliliters in there as my default. What we're finding is with IPA, you have to pump a whole lot more out on the paper because it evaporates so quickly. When you use these engineered solvents that have now emerged, they have a much slower evaporation rate than IPA, so you don't need to wet the paper so much. All you need to do is dampen it. Also, because they're more effective, you only need to dampen it. And then, of course, the number of solvent passes in the wipe cycle, which typically, if we're running solvent, we only run 1 pass unless we know we've got big gasketing problems and we know we've got a mess underneath. So, based on these defaults here, the cost of solvent per wipe cycle is 2 cents. And again, you can change anything you want in here, and it will automatically feed through. Now, the numbers in white, or the cells in white you can change. The cells in yellow are the ones that are calculated, and those feed through right down here. So that, well, A, they're easier to use in the calculations when you're looking at the formula bar, but B, you can see what's being actually used in there. I think I'm suffering myself a rounding error there. So when we go back here, now we know what the cost of our rework is, or the cost of our defects, and we know what the cost of our consumables are. So we plug in our current first pass yield. Pick any board you want. Maybe it's your tougher board like Edward alluded to earlier. People seem to be using these on their tougher boards. Maybe it's on an easier board. Put in your yield, put in what you project for yield. Do you project you go from 80 to 90? Maybe you go from 80 to 85. You want to be conservative. This here gives you the percent improvement in yields. That's pretty simple math, as you can see. Now, what's going to be a very important key here for the user is these 2 cells. The number of defects, or the percentage of defects requiring the simple rework, and the percentage requiring the complex rework, which you pull from your quality databases, your defect Paretos. And I'm very optimistic here when I say 90% of the defects are simple and 10% are complex. That's probably an inverse ratio to reality for a lot of assemblers. But anyway, you can change these. You can say they're 50-50 if you want. You can say they're 90-10. You can say whatever you want. And what this does was now calculate you the savings and yield improvement, and rework reduction, in other words, per print. So if you were only going from an 80 to an 85% yield and your defects were split 50-50, you'd be saving 63 cents per print in rework costs. So I'm just going to return to my defaults here before we go on. And right now my defaults show me saving 35 cents per print in rework costs. Now, productivity, we want to look at our wipe frequency. What's your current wipe frequency and what's your projected wipe frequency? There are some guidelines for it in the magazine article, I believe, but basically you can go 1.5 to 2 times the number of prints before you wipe when you're using the nano coating. And this is a brand new webinar. If you tuned into any of our other webinars, I think we showed you the difference between wipe frequencies and the impact they can make. I've also got some new data where we can show you the difference on wipe frequencies and the impact they make. So right now, if you're wiping every print, you can take it out to 2 or 3 prints. If you're wiping every 5, you should be able to take it out to at least 8 or 10. If you're wiping every 20 prints, you should be able to take it to at least 15, more likely 20, because the bottom of your stencil is staying that much cleaner. So this just calculates the percentage reduction in wipes, and this uses your cost of wipe or paper and solvent per cycle to give you the savings in consumables per print. So at this stage, we're only looking at 1/2 cent per print. But think about how many prints you do in a year, and those cents add up. So right now, this is actually going into rounding error. We're looking at this 35 cents per print savings. In these white cells here, we input the cost of the NanoClear and the cost of the application. Typically, NanoClear is about $25 per 2-part packet, and if you order it in quantity or if you order it online, it'll probably cost you a little bit less, so you can change that to your actual cost. And the cost of the application. If you are having your stencil vendor apply it, he's probably going to charge you $20 or $25 for the application fee. If you want to choose to do it in-house, you can put in 0, or you can say, well, I've got a $20 an hour check and it takes him 10 minutes, so I'm going to put in, $8 or something like that. So you can put whatever you want in there. And what this now returns to you is the payback and the number of prints. So say the application cost us $10 and 99 prints, the cost of that nanocoating is paid for itself based on some of these assumptions. If we go to $20 per application, we're paid back in 128 prints. If we go to 80% of the defects are simple and 20% are complex, we're paid for in 78 prints. So I think this gives you an idea of how to use this calculator. Now when we get down here to the annual savings per SMT line, we wanted to know the number of prints per hour. I'm just going to go back to those defaults so they calculate out all right for us. If we say we're doing 60 prints per hour, that's a 1-minute tax time. That's actually kind of a slow tax time for most lines, but again, it depends on what you're building. So our assumption here is 60 prints per hour, 80 hours per week, which is only 2 40-hour shifts. I know a lot of places run 24/7. And the number of paper roll changes per week. And we're estimating about once per shift. That's where that number 10 came from. And the time to change the wiper roll is about 5 minutes. It depends on if your wiper roll, if your operator reacts very quickly when the machine alarms out on being empty paper. If your paper is stocked near the machine, the ease of threading it through the rollers and platens and getting it back up and running. If your operators are slow to react, if your paper is back in a tool crib or farther away, it's obviously going to take you a little longer to change the roll. If you've got some of the quick change mechanisms that are out there now, it's going to take you less time to change the roll. So basically put your own time frame in for minutes. And the scenario we've got here where we actually changed some of these numbers but not quite enough. There we go. Now we should be back on par. Your annual cost reduction is $44,000. And that's just in consumables. So if you have saved that much time over the course of a year, that gives you 43 extra production hours per year, just on not having the downtime to change it and not having to wipe so much. So what can you do with 43 additional production hours per year? That's like a whole shift week. Based on the inputs of the number of prints per hour, that says you could build 2,600 more PCBs in that time. Let's say you're only running 80% efficiency. You can still build 2,000 more PCBs, multiply that by your average sales price of your PCB, and you can monetize that into the cost savings as well. So there are a lot of different things you can do with this calculator. We tried to keep it as simple as possible. We tried to keep machine depreciation and direct labor, all that stuff out of it. If you want to add it feel free. Like I said, there's not a single locked cell on here, so you can see how everything's been calculated. And again, it's on Aculon's website, or like I said, it's on a rotating banner that I change up every couple of months, so you can find it on the Shea website if you'd like to look for it there. So these are just a few more shots of the cost calculator for those of you who will be just viewing this in PDF and don't have the luxury of listening to it. Now, when we talk about print performance improvements, we've shown some pictures before, we've shown some data before. This is new. And what we're looking at here is production boards. And this is a 0.4 millimeter QFN in production. It's being printed on a 4mm stencil. Look at the difference in print quality. Now, these photos were taken through a microscope and blown up, so they're a little grainy, but you can still see big, fat, sloppy blobs of solder. It looks like we've got a wet bridge going on there compared to much crisper prints. Notice also, process engineers out there, the silk screen. That's right in the middle of the device, and the silk screen out on the corners of the device, and the via right there, and the silk screen right there. All of these are shimming up the stencil and causing a lot of gasketing problems. And that's probably one of the reasons this print looks so sloppy. When you go over to the side with the NanoClear, because NanoClear is repelling the flux instead of letting the flux that oozes out on bad gasketing stick to the bottom of the stencil, we're getting much crisper prints all the way around. Compare this side with this side. Compare the top with the top. And it's still the same exact component. They just pulled the stencil and nano-coated it. You can see the silk screen and everything is the same exact component. Now this is very interesting. This is a 0.5 millimeter QFN, and they're trying to print it with a 5mm foil, which is a lot more challenging. Usually when we see 0.5 millimeter pitch on any leadless device, that automatically signals a 4mm foil or a step down to a 4mm. So this is interesting. We see better print quality, obviously, especially if you look at the sides, better print quality. They also, on the production line, to test the assertion that you can extend your wipe frequencies. This is without NanoClear, running a wet-dry wipe every 3 prints and a wet-dry vac every 6 prints. They almost doubled the wipe frequency here. They went wet-dry every 5 and wet-dry vac every 10. So even with double the wipe frequency almost, with the NanoClear, you are seeing much crisper prints all the way around the device. So that's pretty impressive. So that shows us that we do have better print quality, that we can double or extend our wipe intervals to almost 2x, and we've still got design issues where these friends of ours in the design department put silk screen right around the corners of the device to shim up the stencil and give us gasketing issues. So this, to me, this picture speaks 1,000 words. It's very impressive. So just summarizing those tests, the SPI yields on that board instantly with the inclusion of NanoClear went from 60 to 75%. Minimally, you can call that a 15% yield improvement, or you could call that a 25% yield improvement because 15 on 60 is 25%. For the 0.4 millimeter QFN that was on the 4mm stencil, the average height reduced from 120% of the thickness to 97%, so it was definitely more in control. Again, the NanoClear was much more forgiving in cases of bad gasketing. The average transfer efficiency dropped from 1 to 125. Again, more in control, same board, same device, same stencil, just NanoClear treated and more forgiving to the gasketing issues. When we look at the 0.5 on the 120 micron or the 5mm foil with extended under wipe intervals, we still saw the height reduce from 134% to 120. We still saw the transfer efficiency reduce from 138 to 125, and all the min-max ranges improved also. I don't want to just keep running off statistics, but everything about this improved due to the cleaner stencil bottom and apertures and the way the nano coating repels the flux in the cases of bad gasketing. So now this brings us to a big question that everybody asks. Okay, we wipe the NanoClear on the bottom of the stencil, but does it get inside the apertures? And the answer is yes, a resounding yes. It's hard to characterize because it's so thin. It's difficult to see even with a number of different microscopy techniques, but transmission electron microscopy has been able to nail it down for us. So I'm going to turn this back over to Edward and Mario for a few minutes as they walk you through the TEM results.
Great, thanks, Chris. That was very insightful. So yes, we've had this question a number of times, and the best way to do this was basically a TEM study that we did. My colleague Mario Gattuso is the product manager here for electronics. Mario, why don't you take everybody through what we did?
Sure. So as Chris mentioned, we get the question all the time, does NanoClear coat the aperture walls? And due to our background and knowledge of the chemistry, we know inherently that it does, but how can we need to find a way to quantify it. And by doing the TEM, or the transmission electron microscopy, we're able to prove that. And so in order to do this on a stencil, you actually need to take the sample, whether it's nano-coated or not, and you coat it with chrome, then a carbon layer, and then platinum. And in doing so, you essentially create a stack of material, which you can cross-section and analyze, which allows you to identify if there is a nano-coating on the stencil. So if we can go to the next page. So we did 3 sample configurations, or 3 will be presented here. A stencil with no coating that was freshly cleaned, a stencil that had just been coated with NanoClear, and then a stencil that had been coated and had gone through 15,000 print cycles and 5,000 clean cycles. So what you see here, to hopefully make it clear, is a cross-section of a nano-coated stencil. So the bottom, the dark part that is slightly mottled, which actually shows the grain structure of the steel, is the stainless steel stencil. And then above that, the thicker layer is chrome. And between the chrome and the stainless steel, you'll see kind of a lighter layer in between. And that, if you actually measure that, is 1 to 4 nanometers thick, and that is actually a layer of nano-coating. So the reason the stack of materials is to help to identify the layers of material. So carrying on, we have 3 pictures of sidewalls of stencils here. The top left corner is a bare stencil, which was cleaned, and you can see to the left is the stainless steel, where it says no nano-coat is stainless steel. The lighter stripe is the chrome, and you can see there really isn't, there's just a firm boundary. There's really no layer in between the chrome and the steel. So there shows that there's no coating there. And if you go to the bottom left, that is a nano-coated stencil that we tested, and you can see between the boundary layer of the chrome and the steel a thin white layer, which when you measure it is between 1 and 4 nanometers thick, and that's indicating that the nano-coating is present. And in the bottom right is the stencil that was nano-coated and had gone through 15,000 prints. You can still see that the nano-coating is present. Above there's some contamination from the stencil use, but the nano-coating is still present on the stencil in this cross-section. So to sum it up, the TEM confirmed that there is no coating or any substance on a cleaned stencil with no nano-coating. The TEM confirmed that the nano-coated stencils, both on the bottom side and in the aperture walls, has a nano-coating which ranges from 1 to slightly under 5 nanometers thick. And even after 15,000 prints and 5,000 under stencil wipes, the nano-coating remains intact, both on the aperture wall and the bottom side of the stencil. And obviously there's some contamination in that picture that needs to be addressed, and I'll let Edward get into that.
Great, thanks, Mario. And so yeah, it's a common question, but we've known for a while, and now we've got physical validation that the apertures are treated. One of the things that we also saw in that some of those very close-up images is the role of cleaning and how important it is. And maybe Chris, you know, we've done some work on this over the last 5 years. You can talk a bit about some of the best practices that you've seen.
I'd be happy to. When we talk about best practices in cleaning, first let's talk about durability. We've been working on these for about 5 years, and regardless actually of the type of nanocoating you choose, all these guidelines do apply. The softer, less abrasive under stencil wiper paper, such as the Eco-Roll that you get from Deckersawa or the HyperClean that you get through other distributors, which we have a picture of on the right here, has these little pockets that can help grab the spheres, and it's a softer material, it's less abrasive. If anybody's tuned into our webinars before, we talk about the coarser rans and polys like the Green Monster or the DuPont Santara, that when you're using an uncoated stencil, you really need to scrape the bottom of it and scrape it well. But when you're using a coated stencil, the last thing you want to do is really scrape at it. We often use the analogy of taking a steel wool or a Brillo pad to a nonstick frying pan. You're going to pull that nonstick surface right off. But if you're not using a nonstick frying pan, a soft sponge doesn't get anything off of it. So you really need to now think about the coating on your stencil or not coating on your stencil and match your paper to it. And the most expensive paper out there is not necessarily the best anymore. So you may actually realize a cost reduction by switching from a premium paper to something like an Eco-Roll. Now again, using a solvent wipe rather than a dry wipe is the best because you definitely liberate the particles out of the apertures better, and you dissolve that flux that's building up on the bottom of the stencil. When we saw in the 15,000 print stencil with the 5,000 automatic wipes with IPA, what we saw in that TEM was a thin film. Most lead-free pastes are not soluble in IPA, and what they will do is kind of react and get a little gooey instead of completely dissolving, which is why Kaizen and Zestron now have engineered solvents that have been designed for wet paste cleaning, both in the printer and in the stencil cleaner, and for misprint board cleaning. We always want to use pH neutral cleaners if we can. Anything highly alkaline is likely to attack any nanocoating you have. The general guidance is a pH less than 9 for whether it's fluoropolymer or SAMP nanocoating. A lot of semi-aqueous stencil cleaners are running pHs of like 12. That's not advised if it's just going to wear your nanocoatings away faster. If you are kind of pinned down into this, you can always get a small handheld ultrasonic cleaner for a few $1,000s and use the proper solvent on it. And again, reduce your under stencil wipe frequency. The fewer times you wipe it, the less likely you are to abrade it. And don't forget, you can double the number of prints between wipes, so it's really just a waste of time and money if you don't reduce your under stencil wipe frequency. Now when we look at dry wipe versus solvent wipe, this was a situation that we ran these tests up at Vicor. We treated the flux, we had the paste vendor treat the flux with UV tracer dye, and this is a 0.5 millimeter BGA. We ran 10 prints and did a dry wipe, a dry vac wipe. And then photographed it under black light. As you can see here, you're spreading with a dry wipe, you're spreading that thin film of flux across the bottom of the stencil. When you're nano-coated, you're not spreading nearly as much flux across the bottom of the stencil. There's two reasons for this. First of all, you didn't get as much flux on the bottom of the stencil because it was repellent, and second of all, the stencil is giving up the flux to the paper much more easily because it's repelling it. Now these pictures came out great because We had the flux treated with UV tracer dye, and we were able to take the pictures in the dark. We constructed a little hut out of tote lids. The next set of pictures we took in a lab where we had overhead fluorescent lights and didn't get quite as much contrast, but they still tell a good story. When we do a dry wipe, these stencils are all coated with NanoClear. When we do a dry wipe, we can see that these apertures are clear. Now the smallest aperture, this is the Jabil test vehicle, the smallest aperture is 3 mils wide, whether it's a rectangle, a circle, or a square, and they go all the way up to 15 mils. So when you look at this closely, we didn't color enhance it. If we did, you'd see it a lot better, but this is just actually as shot. You can see after 4 prints and a wipe, you can start seeing that after that one dry wipe that the flux is starting to streak across the bottom a little bit. Now when we used IPA, that was a complete and total disaster. This particular no clean lead-free paste we were using, which is very popular, does not play well with IPA. IPA actually gums it up. You can see on the rectangular apertures, it plugged up the 3 and 4 mils. On the circular apertures, it went 3, 4, 5, 6, 7, 8 mil apertures even getting plugged up. And you can see a lot more smearing of the flux. Now, if you look at the solvent wipe, you see no apertures are blocked, even down to the 3 mil apertures. None of our blocked, they came out nice and clean, and no visible film remains. This is the ideal situation. This is what I've become calling the double play. If you're using a solvent wipe in conjunction with a nano coating, you are running the best possible print process you can. Because after you wipe, this is what your stencil is going to look like, which I'm sure everybody would agree is better than this or even this. Now, how do we check compatibility with IPA? Well, if you run an IPA as a solvent and your printer and you're running it as a solvent in your stencil cleaner, the NanoClear is 100% compatible with it. It's not a problem. The problem is often the solder paste. If you want to see if your paste is compatible with IPA, it's probably the simplest experiment you can run. Fill 2 beakers with IPA and throw the paste in. You'll see the lead-free paste I had here stays in its original form. Even with agitation, it didn't move. The tin lead paste dissolved quite readily. This is because the old tin leads were made out of natural rosins, and quite often solvents in those pastes were ethanol-based or alcohol-based. When we moved to lead-free 10 years ago, we started formulating paste with synthetic resins, and they do not react well with IPA at all. So we've had a few cases where people have had aperture clogging on their 0105s or 0201s, and they nanocoat the stencil and they still have aperture clogging problems, at which time we ask, what are you using for a solvent? And we find out that it's IPA, or even in some situations we found that people are watering down their IPA to reduce their VOC emissions. And resin and water is even worse than resin and IPA, and that's how you're going to build up that film. So my advice is to definitely check the compatibility if you're running IPA. Now in general, if you want to check the compatibility, you should always match your solvent to your soil. So whatever solvent you're using, you should test its compatibility with whatever paste you're using. And again, it doesn't get much simpler than this test. Now we come to the question, do I want to use a fluoropolymer coating or a SAMP stencil coating? They both are very similar in effect, but it depends on your particular application and what you plan on using it for. So if we run down this list of characteristics or attributes, the way the nano coatings are applied, if it's a fluoropolymer, it's sprayed on and thermally cured by the stencil supplier only. If it's a SAMP nano coating, it's simply wiped on, and it can be done by a stencil supplier or yourself. The thickness of the fluoropolymer actually runs into the micron range, 2 to 4 microns. When you're talking about, stencil apertures and the order of 300 microns, 2 or 4 isn't going to make a big difference. But the SAMP nano coatings are literally going on in nanometers, as Mario pointed out to us. Both coatings are hydrophobic and oleophobic, meaning they repel water and oil, and we've heard us use the term fluxophobic, they repel flux. They both have very good abrasion and chemical resistance, with the exception of highly alkaline products, and I have actually at times seen water-soluble paste be a little more challenging on both types of coatings than no cleans. That's just because formulators water-soluble can put all kinds of stuff in there because they know it's getting washed off. Many of the fluoropolymer coatings are visible. Where the SAMP coating isn't, you need to take a Sharpie or a dyeing pen to run it across and look for the beading to verify that the coating is still there and active. When it comes to accessibility, selected suppliers can provide the fluoropolymer coating. Anyone who has licensed it from the originators of the coating. The SAMP coating, any stencil supplier has access to it, or yourself can buy it over the internet at Aculon.com. Are they reworkable if they do get worn off, abraded off, or chemically attacked? The fluoropolymer coating, you are one and done. If it gets worn off or chips off, you need to buy a new stencil and get it recoat and get that stencil coated, so you incur a higher replacement cost. If the SAMP nano coating gets scratched or abraded or whatever, you just pull out another $25 packet and put it back on again. Both greatly reduce the frequency of underside cleaning. And when it comes to the amount of volume that goes on the board, this is sort of interesting. The fluoropolymer will definitely increase your transfer efficiency. We've seen it in numerous cases documented not only by the suppliers but by users as well. And that could kind of be a double-edged sword. If you're running an 01005 and a 5 mil foil, or you're running that 0.5 QFN on a 6 mil foil, you need that increase in transfer efficiency. But if you've always been running a 0.5 millimeter BGA and you're used to getting 350 cubic mils and your process is at steady state, if all of a sudden you're putting 400 or 425 cubic mils down, you may suddenly start bridging. So you may need to consider aperture redesign in certain situations. With the SAMP nano coating, our SPI systems read slightly lower transfer efficiencies, 2 to 3%. Typically, and we've done a lot of work, and there's a paper out there on the SMT knowledge base from the International Conference in Soldering and Reliability in 2014, the Toronto conference, where we actually profiled the deposits. Because you are getting a crisper, straighter sidewall, your SPI machine is estimating a lower volume. I'm not going to climb down on the rat hole of the SPI algorithms right now, but if you're interested in it, it's in that paper and presentation that you can download off of the SMTA knowledge base, or you can download it off of the Shea Engineering website, or we go into great detail in it in the classes and the webinars that we do with SMTA. So bottom line is you will not need any aperture redesign. Can you push the minimum area ratio? Yes, indeed you can. With the fluoropolymer, because you're getting better release, if your process and you know it's good down to a 0.60 area ratio, you're pretty safe allowing apertures at a 5.0 area ratio. The SAMP nano coating, because your transfer efficiency is not going to change that much, you still need to keep in mind your 6.0 area ratio. And some of you out there are asking to yourselves, hey, I thought the minimum area ratio was a 0.66. Recently, some of us in the industry have decided that we should really cite the minimum as a 6.0 because of all the improvements in paste, all the improvements in stencil technology, both materials and cutting, the affordable availability of nano coating, and most pastes are coming out in type 4 now as a default, that we really should consider a minimum area ratio 6.0. And yeah, with the SAMP nano coating, you can probably get it down to a 5.5, but I would not drop it a whole lot more than that. Keep in mind your variation shrinks a lot, so if you're doing something like an LGA where you really need those paste deposits to be uniform, the SAMP nano coating is a great idea. Now the cost is probably the biggest differentiator on these. The fluoropolymer nanocoatings typically cost at least $100 or more, depending on what supplier you're getting them from. I've seen cases where the nanocoating actually costs more than the stencil. And we talked about the SAMP nanocoating price when we looked at the cost savings calculator. It's somewhere between $25 and $50. So there's a big difference there. Depending on your operation, you may opt for SAMP or for fluoropolymer. As you can see in the matrix, there's a lot of considerations to think about. If you have questions, you can always, as to what choice to make, you can always contact any of us, and we'll be happy to walk you through our thought processes on it. So, what's coming up next? This is where I'm going to return it back to Edward, where he's going to give you a sneak peek at what's coming up on the next generation of Aculon nanocoating.
Thanks, Chris. Yes, it's obviously in the last couple of years we've seen emergence of some of these fluoropolymer coatings, and we've had customers, whether it's the OEMs or the CEMs or stencil houses, request us to provide one so that it gives them flexibility in terms of where they're getting their stencils from, and it's from an independent source. So we have developed one. It is a spray and cure type application, so it'll have to be applied by the stencil house. It's a thinner one than the ones you've just described. We're talking about 200 nanometers, so you don't need the aperture redesign, and we would not expect any of the transfer efficiencies to go up in terms of the numbers and some of the concerns you raised earlier. And we've been working with a OEM here on the West Coast running tests, and the initial tests are terrific. So it's got enhanced durability. We're running through 65 wash cycles. It's got increased abrasion resistance. We've been running a lot of abrasion resistance, even with the more aggressive papers that we've alluded to earlier in this presentation. It's got tighter and higher process capabilities on a variety of different apertures and sizes, so we're pretty pleased with that. And what we're ready to do now is basically at Apex go into beta test partnerships in Europe, Asia, and in the US, where we can basically talk about it to a variety of potential customers, and we're going to do that for a limited time period as this gets some traction. The product's NanoClear is available globally. Obviously here in the U.S. We can supply it. Obviously most of the stencil houses here in the U.S. Actually carry this product and have that as an option. Obviously part of the presentation today is to hopefully you'll increase the usage of the nanocoating on your stencils. We have distributors in Asia, and obviously we have partnered with ASM and DEC on a global basis as well. Next week we'll be at Apex, so please stop by and see us at the booth. If you'd like to talk about our next generation of coatings, we'll be happy to do that. If you have questions on NanoClear, we'll also obviously be happy to do that. So let me wrap this up here. So we're excited. I mean, we've been doing this for 5 years now. We're the #1 nanocoating globally by a long way. And I hopefully today from today's webinar you have seen that really it's not just for fine pitch stencils anymore. It can be, the benefits can apply across a broad range of stencils, and we've given you a tool now that you can download from our site to basically calculate those benefits to give you hard justification for this, whether it's the improved quality, the boost in productivity, or the reduction in cost from consumables. We've also hopefully addressed the question some of you may have had, which is, does it coat or treat the aperture walls? Obviously the TEM study does that in very fine detail. And then we've talked a little bit about some of the techniques to enhance durability, and again using the analogy that use a soft cloth on a Teflon or a non-stick pan, that's exactly the case. And so there are plenty of good soft wipe wiper paper out there that is there, and I think as Chris alluded to, the double play, which is using nano coating with engineered solvents, will give you better cleaning at the bottom and obviously improve the print quality. Clearly as a company, we specialize in surface modification techniques, and so when our customers ask us for different options, we do that. And so we are now providing a spray and cure based coating, which will hopefully be competitively superior to what is out there for those companies that are interested in doing that. Obviously, the product is available on a global basis. If you are a company here that gets it qualified in the United States and that production goes to Asia, then obviously we have distributors and partners in Asia that can supply this NanoClear to them as well. So hopefully you'll see that NanoClear enables a high quality, more cost-effective stencil print process. As I said at the start, this presentation will be emailed to all attendees and registrants. They'll include some links for videos, so the instruction video on how to apply. If you are new to this and have never tried NanoClear, then please contact my colleague Mario, and his email is here, and he can potentially arrange for some free samples. The cost calculator, the cost savings calculator, is available for download from our website. And if you have any questions on that, please contact us. But obviously, you can input your exact costs and your yields in the safety and security of your own laptop, and it's not a cloud-based system. So you literally download the Excel file, and you can change the numbers as you wish. The product is available online. If you have questions or volume quote requests, then Mario can handle that. And I know we're getting close on time here, but this is our contact information. And Mario, maybe in the last couple of minutes, is there any questions that we can address from the audience?
Sure. The one question that's come up for Chrys Shea to answer is, how would NanoClear potentially impact a pin and paste printing application?
So the question is, how would NanoClear impact a pin and paste printing application?
That's
the short answer is positively. The longer answer is, when you have pin and paste applications, you're typically running a large aperture, and you're typically running it a little bit farther out from the holes. So you have a longer aperture, and you have longer webs between the apertures. The longer the web is between apertures, the longer the apertures are themselves, the more deflection you see on that web, and the more solder paste you see building up on the bottom side of that web, which tends to make for messy prints and bad gasketing. So we've seen this a lot of times on window pane QFNs, where we have long, thin webs. The coated side, where the Aculon NanoClear is, stays a lot cleaner. So what that means when you're talking about a pin and paste application is crisper prints, fewer wipes, and probably most importantly, less solder balls between the connectors, because you're keeping those long skinny webs a lot cleaner, and you're not contaminating the top of your board with those stray errant solder spheres. So you should see same general quality. It won't affect your hole fill, but it will definitely help with bridging and with solder balling in between the pins. I hope that answers the question adequately.
very helpful. Thank you, Chrys. Another two questions which I can address is someone's asking if they can use NanoClear on a stencil that has been used for several thousand cycles already, and also if a special machine is needed. And the answer to whether a used stencil of 5,000, 10,000, doesn't matter. Any stencil you're using, whether it's new, old, or been heavily used, as long as it's still good for printing, can be nano-coated with NanoClear. Just follow the process, and new or old, it is fine. And then as far as a special machine, certainly not. This is meant to be applied anywhere. It can be applied at the stencil house. It can be applied at any of your facilities. It's a simple wipe process and takes about 5 minutes, and does not require any machines or skilled labor to do.
Gloves. I think all it needs is gloves.
Yeah, that's about it.
And everybody's got gloves.
Let's see. Next question. Chrys, a question for you is someone's asking if you can define what the minimum area ratio is.
Well, minimum area ratio depends a lot on your process, on the quality of your stencil, on the release attributes of your solder paste. For years with the type 3 paste and uncoated stencils, we said you don't want to go below an area ratio of of 0.66. I hope I'm answering the question. The area ratio itself is a measure of the adhesive forces between the pad and the walls because the solder paste sticks to both. So to calculate the area ratio, we take the area of the aperture bottom side opening where it contacts the board and divide it by take the area of the walls, divide it by the area on the board, and that gives us the ratio of the adhesive forces because the paste is sticking to both. Now we used to use 0.66 as an industry standard. I was recently in a meeting with an IPC subcommittee where we think we should start calling out the minimum area ratio as 0.60. I think I mentioned this earlier because we have so much better quality stencils now. Many of them are also nano-coated now, and many of the new pastes that were introduced this year are type 4, and really as technology progresses, our metrics need to progress as well, so we're now calling out minimum area ratios for most processes of 0.60 instead of 0.66. I hope that answered the question.
Thank you, Chris. Next question is, someone is wondering if we can confirm that we said the Green Monster under stencil wipe is in fact abrasive.
It is certainly one of the more abrasive papers out there that we've seen. So we have tested that here on abrasion testing, and we've tested that against something like Dex SMT or the Eco Roll, and we certainly see that there's a improvement in durability if you use the soft papers, some of the Eco Roll and the other ones that Chris mentioned.
Here's a question we get often, Chris. Should you nano coat the squeegee blade?
And my answer is always an emphatic no. Nano coating lowers your coefficient of friction. It makes the bottom side of the stencil and the apertures nice and slick so they repel paste. We never coat the top side of the stencil or the squeegees because we need the friction on the stencil and on the squeegees to get that paste rolling. If your paste isn't rolling, you're not going to fill the apertures. If your paste is skidding, you're just going to slide right across the apertures. I have not tried nano-coating squeegees in production. If somebody wants to try it, I would welcome them to try it in a laboratory environment. This question is probably in response to the fact that there are a few paste formulations out there that are notoriously sticky. They like to stick to the squeegee, and if they don't drop off the squeegee before the other squeegee comes down and takes the stroke, you end up having to wash and reprint that board. So there are some notoriously sticky pastes out there. Humidity generally makes them worse, but the amount of friction on the squeegee is really crucial. In my opinion and my experience printing over the years, I really like the Transition Automation Permalux squeegees. They're not a client of mine. I do not work for them. I never have. I don't get any commissions or kickbacks. I just think that's the best squeegee money can buy. It's on the expensive side, but it plays well with pretty much all pastes, and these guys have figured out the right coefficient of friction to put on a squeegee. So that's usually what I say. If you want to try putting nano-coating on a squeegee, I would do it in a lab, and I would see what happens before I tried it on a production line. And if you do it in a lab, and it does work out well, or you want some input on the data, please feel free to keep me in the loop.
Okay, thank you, Chris. The next question is from somebody asking, is there a need to adjust the parameter after coating the stencil with NanoClear, as we noted some underside paste bleed out?
Okay, so the question, as I understand it, is once we coat with NanoClear, do we need to adjust our print parameters? I would say no. Run them exactly the same as you had been running them, so you get a good apples-to-apples comparison on either your SPI yields or your end-of-line yields. We see very little bleed out, and especially if you've got boards with bad gasketing, whether it's because you have poor support tooling or just regular old pin tooling, or you've got boards that have uneven topographies due to heavy silk screen, solder mask, trace over mask, whatever. The NanoClear really gives you a big advantage because when you're separating, paste is somewhat elastic, and you've got a tug-of-war going on between the board and the stencil, and that paste is really the rope and it starts stretching. Well, at a certain point on the nano-coated stencil, the stencil just gives up the paste. So it's like a tug-of-war when somebody on one end of the rope just lets go. And so, no, I would not adjust my print parameters. One thing, if you do see more bleed out or you do see fatter kind of prints at the base, I would look at the separation speed. I wouldn't change the squeegee speed or pressure. I would just look at that separation speed, because most of the paste that are newer formulations these days, anything in the last 5, 6, 7 years, typically likes a fast separation speed, and you'll get a crisper print from that. But that's aside from the nano coating. That's just a little side advice for the process. So the short answer is no, don't adjust your parameters.
Okay, thank you, Chrys. Looks like that's about it. I don't see any new questions coming in, and that about covers it.
Okay, well, thank you everybody for listening. Thank you, Chrys, for being so informative in this industry. And as I say, the copy of the presentation will be emailed to everybody. The recording will be on our website, and we'll send you a link to that so that you can download it or listen to it or share it with your colleagues, etc. So with that, we thank you very much for listening, and we wish you good printing. Thank you.